For this project, the University of Vermont has partnered up with Benchmark Space Systems to build a prototype CubeSat. This CubeSat will attempt to satisfy the emerging need for these small satellites to feature propulsion systems that enable precise attitude control. The propellant the team will be using is CO2 to simulate the use of the foaming agent azotic carbamide Benchmark uses in their products. In order to control the mass flow going to the thrusters, a spike and hold pulse width modulation driver circuit is used to effectively open and close 4 lead valves. This will allow the CubeSat to maneuver in 3 degrees of freedom. The microcontroller being used is the Arduino Uno, which has the ability to update code wirelessly for easy testing. The microcontroller will be used as the trigger for the driver circuit, applying a 5-volt square wave from the digital pins of the Uno to the DRV103H chip for a controlled period of time to stabilize the CubeSat for all linear disturbances. This is the final product that our team has come up with. There are still a couple of problems we need to work out. The first problem would be to filter out the noisy sensor information that is coming from the ultrasonic sensor. The main problem seen in the data is these random spikes shown on the graph of the sensor output. The filter that is chosen cannot rely on sorting of data because this is computationally expensive. In order to satisfy our requirement for precise attitude control, a constant false alarm radar is applied to the sensor output signal. The CFAR filter was initially designed in World War II to filter echo noise being received by antennas of radar systems. Since our system is using an ultrasonic sensor that sends out a similar wave to determine the position of nearby objects, a CFAR filter works well. For every 9 data points that are received, the filter searches for a local spike and cancels it out, as seen in the thresh function underneath the CFAR constant false alarm comment. For periods of time that are experiencing just low-pass noise, 8 consecutive data points are averaged to smooth out the error that is being used to stabilize the linear position of the CubeSat. This is the code that is used to implement the filter. The control code is programmed so that all the initial noise is canceled and properly shifts more than 9 bits to fill the dataset accurately. This initial position is recorded and will be set as the reference for the control system to track. In this filter, the 4th previous timestamp is analyzed to determine if the data point should be thrown out or not. If there is not a data point that should be thrown out, then the system reacts on the 7th previous data point, averaging the current timestamp X to XPrep7. The design effectively cancels out the noise of the system as shown in the live graphs. In order to test the filter, 2 procedures were performed to make sure the data being received is adequate for proper control. The first will be a standstill box measuring the distance from the sensor to the box. This graph shows the unfiltered results. And this video shows the filtered results. As shown, the new filtered data properly cancels out the unwanted random spikes. The next experiment that was carried out was the shaky box test in order to simulate rattle of the CubeSat when it is experiencing an attitude disturbance. This graph shows the unfiltered results. And this video shows the filtered results. These tests were repeated numerous times in order to determine if we have an adequate sensor reading. A suggestion for future teams would be to implement an optimal gain controller that can adjust to possible sensor discrepancies if they occur. Another idea would be to implement a sophisticated CFAR which can adaptively set the threshold level that cancels out noise based on statistics of the target that is in range of the sensor.